Hello everybody, I am Matteo Andreottola, I am a structural engineer. I am of course as well part of Rothoblaas and in particular Rotho School. What is Rotho School first of all? Rotho School is a part of Rothoblaas taking care of the formation of internal people but also external people. So we make courses and seminars every year for people interested in the timber sector basically. We have, for example, this year almost 120 courses around the world internationally in 7 different languages. And we decided as well to do these video lessons. These are for us very important. We'll have 9 video lessons this year, free of charge for everybody, because we think that timber is a great material to work with, has some great potential and characteristics, structural characteristics and also beauty, of course. But it is a material that if you want to use, you have to design in the right way, just to avoid issues of durability, to have the right connections in your buildings, and so on and so forth. So we placed 9 video lessons about the 9 hottest topics we think this year, and let's see how it goes. So first of all, I wanted as well to introduce a little bit what Rothoblaas is. Rothoblaas is a company based in the north of Italy. In fact, I'm speaking to you at the moment from Cortaccia, which is a little town from in between Trento and Bolzano, in the middle of the Dolomites, very close to Lake Garda, if you're not from Italy. So a very beautiful part of Italy. You can see as well from the image here where all of our subsidiaries are located all over the world, because we are actually working all over the world, close to where you are. We have 6 main lines, and these are the screws, for example, screws for wood, the plates, the tools, the soundproofing, the fall protection and safety, the tapes, sealant, and membranes for the airtightness and waterproofing. This is why we have an alpine heart but an international spirit, because we are located right in the middle of the Dolomites, but we are as well present and located all over the world with our subsidiaries. As you can see here, we are more than 400 workers in Rothoblaas at the moment. Actually, we are almost 500 as we speak, because we keep on growing and growing. And if as you can see here, but we're going to discuss more in detail also in the video lessons, also this particular mass timber structure here, we just recently finished the construction of this massive and very nice automatic mass timber warehouse that we have here in our headquarters of Rothoblaas. And this will, and actually has already doubled the existing warehouse space that we have in Rothoblaas. So for us, it's practice what you preach. We preach with our Rotho schools around the world to use timber, and also for our own project, we use timber. The use of wood and of timber structure, of course, for us is very important for, as you all know, a sustainability point of view, very, very important. And this is why we preach also the use of this kind of material, structural material in this sense. But of course, as you all know, timber is a material that a lot of people are passionate about, and myself, I'm the first one to be passionate about it. And second of all, it has a lot of very, very good structural characteristics that we'll see throughout the video lessons. And this is why a lot of people love timber, not only because of its beauty, but also because of sustainability and great performance, really. What are these video lessons that we're going to do this year? There are 9 of them, actually. We start with the potential of CLT and mass timber, actually. Then we'll go for durability of timber structure and corrosion resistance for outdoor solutions, waterproofing and airtightness of timber structures, the acoustic in timber constructions, the fire design in timber structures, the seismic design, the composite structure or hybrid structure, a very hot topic nowadays to optimize the use of timber, the innovative connections for timber structures, and last but not least, the installation of full arrest system. Thank you very much, and thank you for your attention. Hello everybody, in the lesson of today we are going to have a look at the fire resistance of the timber structure, as you can see here. So a lot of people, as you can see in the image, they have the fear that timber and wood in general is a combustible material, and therefore the resistance in the fire case is not going to be good. Actually, as we will see in the presentation of today, is exactly the other way around. But why are people so scared about the fire case? As you can see the image, the effects of the fire on cities, on buildings in general, are devastating. And this is why these images are stuck in the image of people. What we are trying to do with this lesson, we are trying to explain why it is exactly the other way around. In fact, I've done this graph for you to more deeply understand the phenomena. And in fact, here you can see that the main issues and main causes for issues in the timber buildings are design issues, for instance. So the timber building is not designed in the proper way. And this is, by the way, the reason why we do this Rotho school in general, because it's very important to build in the right way with timber structures. It's strictly connected with the design issues, also the durability issues. In fact, timber has to be again designed in the right way so that it's durable throughout the years. And also connections are very, very important to design in the right way, because of course it's the most fragile part of the timber structure if not designed correctly, of course. And therefore, you can see that only 5% of the overall amount of issues is caused by the fire case. So we shouldn't be so much worried about fire and the timber structures. Actually, sometimes it's more of an issue when we use another kind of structural type of structure, for example steel, just to give you an example. So you can see here what happens when a timber structure is gets on fire and after the fire is then extinguished. You can see here first of all that the connection is completely exposed, but anyway the timber structure is still standing, so it's not collapsed yet. This, first of all, means that we actually have a lot of safety factors in our design, and we will see the design phase throughout, of course, the short lesson of today. And this, of course, shows you that the structure itself, it has a lot of resistance to fire. Of course, it has fully charred. It's you see, it has burned completely, and but this doesn't mean, of course, that it has collapsed. What has collapsed though in this image, and it's very clear, all the secondary structures, for example the purlins in this case, or the timber boards, the finishes of the roof has although collapsed. So one advice is, of course, very important to design the structure to have the right and correct fire resistance, but at the same time you should be also careful at studying also the secondary elements that you have in your structure, so that you don't have issues and risk of them collapsing on the people inside of the building. Other pictures here of the main structure, you see that the primary beams and also actually here the secondary beams are still up there without any issues, although everything has completely burned. But again, keeping in mind the pictures that we've just seen of the burnt structure, why is it, of course you've seen that it's all charred and the section of the timber beams, it's very much reduced. So why is it still standing? This is the first question that we could ask ourselves. The first answer to this question is right here in front of us. So first of all, in the load case, in the fire load case, we consider lighter weights. So we consider a different loading, which is lighter than the one we consider for ultimate limit states. And why is that? So first of all, you can see that one example is the snow case, so the live load of the snow. Of course, since we have a fire burning inside of the building, the heat is melting down the snow, and therefore the snow is not there anymore. So we can consider also in the physical, in the real case scenario, we can consider a lighter load. Another thing that we should consider is that the live load itself, so the people living inside of the building, of course are evacuated, they escape throughout the fire. And this means that no people inside of the building means a lighter live load, of course. So in fact, you can see here what I've just explained to you, heat and the people escaping. And so even from the real case scenario, it's easy to understand why the calculation is like that. Actually, it's way easier to understand how the calculation works if it has a clear connection with the physical case, so with the real case scenario. But going back to the theory, what do we need in order to calculate the resistance, the fire resistance of a timber building? Of course, in this case, the Eurocode 5 about the timber structures comes really much handy. Also, the Eurocode about the fire design. So these two Eurocodes, they are the main references for the fire calculations. But before going into the calculation and the formulas themselves, is important to understand again the physical phenomenon of the combustion. So when is the combustion happening? When there are three things when three things are present at the same time. In fact, you see that it's easy to explain it with the combustion triangle, which is the one you can see in the slide here. So, of course, you need oxygen. You need a trigger, which is an initial flame that triggers the whole fire. And then you need fuel. Fuel can be anything. It can be the timber or combustible elements inside of the structure itself. The ignition temperature of timber is about 200-250 degrees, and the energy and the heat that comes out of the combustion is, of course, very big. But of course, one case is the physical one. Another case is what we consider for the calculation. Of course, you can see in blue we have the natural curve of the fire case, of course. Initially we have the ignition again, then you see that the curve is going upper and upper because we have what's the so-called general fire. If we have only to study the fire resistance of the timber structure, we don't really consider the ignition phase with not so much heat involved in it. So we only consider the general fire. So the general fire happens only after the so-called flashover. Flashover is the situation after which you have indeed the general fire. But let's go again into the theory, but let's go more deeply inside of, let's take a little piece of a timber section, of course, of our structure, and let's analyze what the charring involves and what it means. You can see different layers in our cutout of the timber section here. You see the black part, which is of course the charred area, so the part which has charred already. Then we have the pyrolysis area, so it's the part which is burning without a live flame, of course, but it's still burning. And then we have the intact wood, so the one that is not charred yet, it is not burned yet. Inside, where we have the intact layer, we have the so-called intact section, so the residual section of our timber beam. So the one that is still resisting to the loads even throughout the fire case. What is the good characteristics of timber? We were saying before that it works better than other structural types and materials in a fire case, and this is the reason. The following reason is very important because, of course, the wood burns. That's something obvious that everybody knows. It's a combustible material, but it's a very good insulation material at the same time. So first of all, we have to say that it burns, of course, yes, but it burns at a constant rate, which is very slow. It's a charring rate which is fairly slow. We will see that it's around 0.7 millimeter per minute, so it's very slow. And the other thing which is very important to keep in mind is that the residual section that we have on the inside of our charred layer retains all of its structural properties. This is because, of course, timber is an insulation material, and therefore it's not conducting the heat inside of it. If we consider the same thing, and we'll see it in the next slides, if we do the same thing with a timber section, of course, in about 15 minutes, it heats up completely, and with a lot of heat, of course, timber, on the contrary of timber, steel is completely losing all of its structural properties. So it's actually collapsing because of the heat itself. So if we see even better here, another section of the timber, you see, of course, the charred part of the wood is losing all of the water that is inside of the wood itself, and therefore it cracks. So it's easy to understand that this part does not retain any structural properties. But we have to add something else, though. Inside of the residual section that we were discussing previously, we have a little layer, and you can see it here, which is the pyrolysis area and something slightly further that has a higher temperature. And just in case, as the engineers always do, just to be on the safety side, we are not considering that part either in the calculation. So we take it out of the game when we have to calculate our neat section. And you will see exactly the same thing in the calculation that we'll analyze together throughout the presentation. So as you can see here in the spec that we have in front of us, different types of wood have a different charring rate, of course. So what are the characteristics that are most important for the charring rate to understand how fast our wood species is burning? First of all, the density, of course, because if you think about it, more density means that there is more material to burn. So, of course, more material to burn means that it takes a longer time. So it means a slower charring rate. Of course, humidity. Humidity, yes, in the sense that, of course, it's slowing down the combustion. Yes, this is easy again to understand. But we have to add that for our timber structures, usually the humidity is controlled and is under usually around 12%. So it doesn't really make such a lot of difference. Then we have, of course, the wood species. If you have a different wood species, then you would have, of course, a different density of the wood itself. So it's very similar to what we've stated before. What does not really change the charring rate at all is the material strength class. This is something that is linked to timber, to structural timber, of course. The material strength class, it has nothing to do with the charring rate. So it only helps the timber structure to have more resistance, but in the ultimate limit state. So in fact, you can see from this little spec here that the wood species with a higher density, they also have a lower charring rate, so they burn in a slower way, in fact. Here you can see better what we were explaining previously. So the difference between timber and steel. and how fast these materials lose their structural properties. And you can very clearly see that among all the other materials, timber is the one with the temperature, which is the red line, of course, here, that is rising constantly. You see that the timber is the material that mostly retains its structural properties. So that's very good. We said that before, that after 15 minutes, usually all the fire that is exposed, all the steel that is exposed to fire and not protected, of course, in 15 minutes roughly, it loses its structural characteristic. Here you can see a zoom in of what we were explaining previously. We don't have only to consider the fire resistance, of course, of the structure itself. It's also very important to consider other factors. So the fire resistance is the R, the first letter that you can see here. Then we have the E, that stands for integrity. And so, of course, if you have a structural wall that is dividing, or a wall in general, that is dividing one compartment to another compartment, that one has to retain its integrity in order not to have the fire spreading from one compartment to the other, and this is why it is so important. As well, also, the insulation means that if we have a fire in one compartment, it's important not to have the heat trespassing the compartment either, because, of course, also an extreme heat can cause, again, fire to spread in the other compartment. So we don't only talk about the fire resistance, but to sum up what we just said, also fire reaction is very important. And we will see what are the materials that have a better fire reaction than others, of course. It's roughly at the end of the presentation. But now I would like to see with you and to analyze with you a little more in detail how the calculation for the fire case works with the timber structure. In particular, here we have our timber section, and you see that here we are trying to calculate what is the residual effective section that is left after the fire case. So it is actually that section that we use to calculate the residual resistance that our timber beam, for example, has after an exposure to fire that can be 30 minutes, 60 minutes, an hour and a half, and so on and so forth. So, of course, we said that the Eurocode is coming very much handy in this case, and what are the differences that we have to analyze together. So there is one-dimensional charring rate, which of course it's easier to calculate because in the case of wood, the one dimension is easy to consider. In this case, charring rate, you see here from the image, d char 0 is the dimension that chars after a set amount of time. It's just a simple, calculation. It's beta 0 multiplied by t. T, of course, is the time of exposure, and the beta 0 is the one-dimensional charring rate. You see that if we consider also the corners, though, it's easy to understand because also the physical idea, it's quite clear in your mind. Of course, if you think about a corner, it is attacked from fire from two different angles. And in that case, it's easy to understand why it's burning in a faster way. So again, it's easy to understand why the charring rate, which is in two dimensions, where a corner is, it's higher than the one-dimensional charring rate that we analyzed before. In fact, you see that it's exactly the same formula, but in this case, we consider in the formula the beta n, so again multiplied by the time of exposure. So of course, we will see now what is the difference between this beta 0 and beta n. Of course, you see that beta n is a higher value. In fact, to consider the higher charring rate in the two-dimensional case, we consider in general a higher rate, millimeter per minute. So in this case, see for instance for hardwood that the beta n that we consider is 0.7, again millimeter per minute. So in this case, there is another choice that you can do. You see that, of course, on the left we have the initial section that we have in timber in our structure of glulam in this case, and you see that in this case it's burning from all directions. You see what's happening in the first example with chamfers. So you could consider the radius chamfer in the corners. In this case, of course, you're more precise, but this means that the calculations are way harder than to do, really. Another thing that you can do that is often used by engineers, we said it before, engineers tend to simplify things and to be on the safety side all the time. So one way to simplify the whole calculation, of course, is not even considering the chamfer that you have where your corners are. But in this case, you just consider a smaller section that can stay within your section with chamfers, considering only, of course, the square corners in this case, which is, of course, way easier than to calculate. What is the final verification that we have to do? As always, we need to calculate that the resistance of the section that we have is higher than the loads that we have on the same section. Of course, that's easy to understand. We said it before, in order to calculate the loads that we have onto a beam, you should consider the exceptional combination of loads, the one for fire in particular, that I've reported here in the slide. And the other thing is the calculation, of course, of the resistance. In the calculation, in the case of the resistance, it's easy because you should consider a K mode that is equal to 1. Again, also your gamma m in the fire case, it's again equal to 1. So it's a very simple formula, the one that you see here on the screen. And you see that you consider a higher characteristic resistance of the timber section itself. So explaining the same thing using simpler words, it's as if your timber structure would have a higher resistance in the fire case. So not only the loads that we consider are lower, but also the resistance that we consider for wood is considered as to be higher than the one in the ultimate limit states, according to Eurocode 5. So this comes, helpful into the fire design of our timber buildings and wood buildings, of course. You see here what we've just explained, and you see that the characteristic resistance that we have is multiplied by this K fire. And this K fire is always higher than 1. So it means that it enhances the resistance. This factor here enhances the resistance of in the fire case, of course. Sometimes 1.25, it becomes in connection only with fasteners, for example, in shear only 1.05, 105, but still always higher than 1. This is, of course, mostly referred to engineers. But I would like to explain it to all of you because actually the formulas that you use for the fire calculations are quite easy to understand for everybody with a little bit of a general knowledge for math, really. So you see again here, in order to calculate the layer and the part of the section which has completely charred and that you should not consider in order to get the neat section, so the effective section that you consider for your calculation, you have, of course, to take away
your dchar n, so in this case the part of the wood that has charred in that particular time, of course, that you have to calculate for. Then you have to add, of course, also this other thing, d0 multiplied by k0 again. K0 though is equal to 1, so d0 is only 7 millimeters. So again, just to repeat the same thing in easier words, you take away to your section, just to calculate, of course, the neat section, you take away the charred part, plus those 7 millimeters, which is, as we said before, the part which has a higher resistance, and so we are not sure that that part is retaining 100% of its structural properties. So just to be, again, on the safety side, you take it out as well. And you're only left with the effective section on the inside, basically. Again, we said it already, density, and it's one of the key factors, but we've explained now how to calculate the effective section. We said it also before in the first graph that we analyzed together, that one of the most difficult and the most hard thing to do here are the connections. So the connection, we should always design them in a particular, paying a lot of attention, especially for the fire case, but also in general. So you see here two examples of a connection on fire, of course, between two timber structural elements. We have on the left one connection which has exposed steel plates on a timber section. On the right, we have almost the same steel plates, which are though completely hidden inside of our timber section. It's easy to understand which one is working the best, of course. It's always important to hide all of our steel parts inside of the timber so that the timber is protecting the steel from fire. And this is a very good sum up of what I was saying before. It's easy now to understand why wood is working so well with in the fire case, because of course we use wood, the wood material, to protect the steel from fire. So this really is a very good sum up of what I was meaning. In fact, have a look at this image here. You see a partially unprotected connection, and have a look here at the bearing of these steel dowels. Of course, the steel dowels heated up, and you see that the bearing is lower because if you heat up the dowels, you see what happens to the timber, of course. Imagine what's happening when you have some steel plates inside of the timber. So they bring inside of the section the heat, and of course heat is not making things better at all. So sometimes when you have a lot of steel plates inside of a timber section, it's good to do some further verifications, of course, because it can change the easy formulas that we analyzed before. One other important thing is the minimum distances. You all know that minimum distances in general are super important for designing timber, because even if you're not considering the fire case, it's important to consider the right minimum distance in order to avoid brittle failures. But also when you do the fire design of a building, it's important to consider the right fire, the minimum distances for fire. Since we've understood that the timber is charring, so you're losing a part of it, in the particular case in which you have the dowels exposed, so they heat up and you see what happens in the image, in that particular case it's important to increase the minimum distances from the edges so that you're safe even after the reduced and the charring of our wood around it. We are still safe and we don't risk to have a brittle failure, of course. And you see what I mean with enhancing the minimum distances. You have to add this A fire, so an extra dimension to your minimum distance. Another thing, though, that I strongly suggest is, again, protect your timber dowels, but also the plates, using timber, for example, again, timber dowels or timber panels, in order to hide completely the steel inside of the timber. This helps a lot to increase the resistance. It's, as we were saying before, it's not only important to talk about the fire resistance, it's also super important to consider the right fire reaction. And I connect to what we were explaining previously in this same presentation. In fact, you see here in the image the Grenfell Tower in London. Actually, we had the same thing happening also in Milan to another high-rise building, not with a timber structure, but we had the same issue. So the issue here is a ventilated facade in which the wrong materials with the wrong fire reactions were used, and with a very small cause, so a cigarette thrown in the wrong way in the wrong part of the building, or too much heating as well during the summer months, you risk having such big damages. So imagine what is damage actually means. This means actually that 100 and more families are losing their own flat. So it's something that, of course, we have to avoid at all cost, really. So let's analyze the issue more in detail here. You see what happens with a ventilated facade. Of course, the ventilated facade is very important for your building envelope in order to have cooler temperatures inside of the building. But though it can be a highway for the flames to go up, and actually even to spread from one compartment on the lower floor to the upper compartment on the next floors. So that means that the fire can spread very quickly. One important thing that you could do, for example, is placing some interruptions of this ventilated facade, still having, though, the airflow that can go up in a continuous way. This at least help to avoid these things. Another, of course, thing that I strongly suggest, though, to avoid completely the issue, is using materials which are the right ones, so the ones with a good reaction to fire. You see a lot of smoke here as well, and you see that reaction to fire, we will see it throughout the explanation in a second, means also that you're not producing such a lot of smoke. Usually a good reaction to fire means also that the materials are self-extinguishing and do not produce droplets of fire and do not produce too much snow. This is, by the way, is another tower, the one in Milano, Torre del Moro, the one that we were explaining previously. So we've explained again what are all the characteristics that you have to keep in mind. Let's jump straight onto the solutions that you can use. Of course, for sure now, Rothoblaas, we are lucky that we have already some solutions ready for you. And the first one, for example, is using products which are not combustible at all. So you see what is the name of this product. You have an A2S1D0. At the moment, this maybe does not mean anything to you, but A2, these initial two letterings that you have, means that the product is not combustible at all. Of course, instead of being, in this case, a membrane that can catch on fire, in this case, we have an aluminium barrier. And therefore, you know, the aluminium is not a combustible element. So in this case, it's an element that cannot burn at all. What are the other two characteristics that we have in here? The next one is S1. S stands for smoke. So it means that it's not producing so much smoke, which is, again, important, and you've seen before why. D0 is just as important because D stands for droplets, in this case. And you know what happens when you try to burn plastic. It produces droplets on fire. And this is exactly what we have to try to avoid when designing a timber structure or a facade in any way. because droplets on fire, of course, can spread much faster the fire on the whole facade of the whole ventilated facade of our building, of course. So what are other membranes that we can use, for instance? We have the so-called EVO membranes. EVO stands for higher quality, stands also for monolithic membranes, and you've seen in previous presentation what the difference is between microporous and monolithic membranes. In this case, the EVO products, they have a better reaction to fire. So in this case, these are combustible because you see that there is a B, and the first letter is a B, so it means that it's combustible, but at the same time is self-extinguishing. And you have an S1, so it produces just a very few smoke, and it produces, of course, no droplets. Another thing that you could do is going on YouTube and check out the videos that I'm showing to you right now. You see in the upper part a microporous membrane which is not designed for the fire case. So you see droplets, you see smoke, you see that it's not self-extinguishing. In the bottom case that you're seeing right now, you see that the membrane initially catches on fire, but then immediately it's self-extinguished itself. So it does not burn. You can try it, by the way. It's simple to try with 2 samples. This little test at your home, of course. What about connections, though? We said before that connections are, again, one of the main and more complicated things to design in the right way. And of course, in the fire case, since there is always a little bit of tolerance in between the structural element and the timber wall, in this case we have a CLT wall in our picture here. So it's always better to protect that part with something that is, avoiding the flame to get into the connection and increase the temperature that we have inside of it. So what do we use? The general name is a coking strip. So it means a strip that is increasing its volume with heat, and basically by increasing its own volume, it's protecting and insulating more the inside of the connection, of course. In this case, you could use the fire stripe, for instance. That is a physical strip that you put around the connections, the connection. Otherwise, you could use a fire sealing silicone, which has similar characteristics, but you put it down maybe in a faster way. It's like silicone, of course, or even fire sealing acrylic. So different things to pretty much doing to have the same solution. We said it before that in order to have a certified solution, also an EVO product like Truspier EVO UV 210, which is a membrane that we have for ventilated facades and for walls in general, using also this particular tape, which is the front band UV 210, you can have a certified facade that works well for the fire case, for instance, having a code, a characteristic that is BS1D0, just to connect to what we've explained before. Remember also 2 other products that you can use for the fire case are the taps, very easy things, but are so important to protect your connection from the high temperatures of the fire case, of course. By the way, they completely hide the connection itself as well, so that you're sure that also the visual quality is better. So this is good for architects, this is good for engineers, it's good for the fire case in general. One other important thing that we'd like to explain to you, you know how important the acoustics are for timber buildings and for buildings in general. Just to go a little bit more deep into the acoustic and fire, You all know what xylophone is. It's that strip that you place in between walls and floor structural elements to avoid the passage of vibrations and noise. In this case, we're lucky. Actually, we studied it. It's not luck in this case that this particular material has a very, very similar charring rate to the one of timber. So you can use it also in the fire case with no issues. We've done fire test with the Rise. In this case, you can see some images. And I would like to point out, though, how important the details are in the fire design. So the devil is indeed in the details. As I always say, you see, in fact, what we've noticed just before the, continuing with the fire test, this little gap in between the floor and the CLT wall. So first, we wanted to completely hide it and fix it, but actually, after a little bit of thinking, we said, let's actually keep going with the test with this little gap, as if you would have on a real structure if you're not careful, and let's see what happens. And this is the result that we had. So you see how the flame was capable of entering through that gap and, of course, expand the fire also outside of the compartment. So this is why it's so important to use coking strips, as we were saying before, that with heat are expanding and are definitely a solution for these issues here. So what do you have to do if you have a typical connection between a CLT panel and another? This is one of the typical connection, I would say, that you could have possibly with CLT. You see that this butt joint connection, half-lap joint connection, you have a partially threaded screw fixing the whole thing, but the question here is what products could I use in order to avoid the passage of hot gases in general, high temperature, and the spreading of the flame as well. So what do you use inside here? So you're lucky that we have our solution. You always need to place on the side that is on which you could have the flame burning. You should put a coking strip. So, for example, a fire sealing silicone on some of the other products that we mentioned earlier. On the other side, you need a product for the airtightness, because if you do the airtightness in the right way on the other side, where it's not burning, of course, it's not burning because you have your floor finishes and you would never get to the tape, of course. In this case, there is no suction of air, and if there's no suction of air, also the hot gases staying in the compartment where the fire is and cannot spread the fire to other compartments. You see here another solution, exactly the same concept. So fire stripe on the bottom part, and an expand band, which again is an expandable material, which is making sure you have the right air tightness of the building. So same exact concept with different materials. Thank you very much. I hope that this very short lessons on the fire resistance and on the fire reaction of buildings in general was interesting. I'll leave you here my email. I am Matteo Andreottola. I'm available for any questions. In the meanwhile, I thank you very much for your attention, and I'll catch you the next time.